All right, recording is rolling. Welcome to Wednesday, August 16th. I did enjoy reading the cards, the note cards. A lot of you guys turned to the great show yesterday. You didn't have to, but saw you guys had a lot of cool things going on, a lot of cool interest, a lot of cool things you guys are doing. So that is awesome. Hopefully, this class, in one way or another, helps you out for sure. Right, so today's a little bit of a weird day because there are these class meetings. So those are in the auditorium. So I wanted to come up with activities that'd be definitely worth the time to be here, but also not get all my class and students out of alignment. And I think I managed to do that. So we're going to do a few algebra puzzles got on the line up here. You guys are already solving those. You guys have your notebooks out. Awesome. You guys are ready to go. If you guys don't have notebooks for any reason, then a couple things. One is I got a stack of paper right here. And another thing is you guys do have planners. That would be a good thing to put in your planner to book a notebook, but I think you guys are sharp and on the ball and ready to go. We're going to do a little bit of dimensional analysis. If I need to go back and do some more of those with you guys next week, we will. Some of the activities I lined up this week, we're going to kick to next week. Circle measurement, graphing, trigonometry, say that for Monday, Tuesday stuff, right? Got an activity for you guys that we'll eventually get to. Right. So I do want to solve those algebra problems with the guys, but here. I know I was going through some of these posters, and I think I ran out of time last. I could have used a few more minutes class yesterday, so let's go through and hit the ones I didn't do yesterday. Did we do this one yesterday? Okay. We talked about accuracy and precision. So if something's accurate, that means it's giving you correct values. If something's precise, that means it's giving you consistently the same values, but also in terms of numbers, like you have many decimal places to work with, right? Like for example, here, imprecise versus precise. Here's the speed of light. That's c. C is the speed of light, right? I might call the speed of light 3 times 10 to the 8 meters per second. That's true to 1 digit. That's true to 2 significant digits. That's true to 3 significant digits, right? But the more you go up this page, the more and more precise you're getting, like the more precision you're getting, right? You guys get that? Right. Here's the exact definition of the speed of light as like this made it. Okay. Right. What does it mean for something to be both accurate and precise, or just one or just the other? Okay. So if it's both accurate and precise, you're getting the correct value, but over and over, right? So suppose I put this 1 kilogram mass on different scales and tell me 1.0 kilograms, 1.01, 1.00. Okay, so it's like the same readings over and over. That'd be both. That'd be this guy here. Okay? What if I put it on 3 different scales? I'm getting like 1.0 kilograms, 0.9 kilograms, 1.1 kilogram. That's not very many digits to work with. They're all kind of spread all over the place, but they do average out to the correct values. So that'd be not precise, but it would be accurate. Okay? Suppose I got 3 different scales. Like I know the value of this is a kilogram, should be pretty close to kilogram. But what if I have a scale I've calibrated, it says like 1.15 kilograms. Like, okay, that's off. I try it again, it says 1.14. Try it again, it says 1.15. Like, okay. So it's telling me the same thing over and over again, but it's probably just not calibrated correctly. So that's like example this one here. And then if it's neither precise nor accurate, it's giving you all over the place. Just got that. Did we do this one yesterday? Dimensional analysis. Okay, yeah. We'll do a couple of these today. So that was nice from yesterday. I got a couple examples there. Did we do scaling?
Yes.
We did do scaling. Oh, okay. All right. So quick recap, just for the video. Okay. So if you scale something up, let's say I got a little box here, scale it by a factor of 3. That's a linear factor of 3, right? But anything related to area, like if you're painting it or something, right, it's going to scale it by a factor of 3 squared because surface area is a 2-dimensional concept. Anything that's a 3-dimensional concept, you have to take that scale factor up to 3 dimensions. Right? So the large crate has like 27 times the volume. Right? AP loves to ask questions about like, if you scale the size of a planet, how's the gravity field of the surface at surface change? Right? That's this classic AP question. Right? And then you have to say, well, let's see, I know the volume and therefore the mass of the planet is going up probably something like this, but your distance from the center is going up something like this, and then you have to like juggle both of those at the same time. To think, right? Okay, so just think ahead, right? Here's basic. Did we do a basic algebra problem? Right. I mean that's what we're about to do anyway, but let's run through this. Right. So you start with that. Like okay, square root both sides. Oh, getting a plus or minus. Like square root of 4 to be either one of these. Right. Multiply the 5. Add over the 11. Divide down this coefficient. Boom. Right here. You take either one of these answers, you plug it in there, and you should get 4, regardless if you plug in 1/3 there, plug in 7 there, right? You should get 7, right? And we're about to do that anyway. Okay. Y equals mx plus b. Real good to know this by heart, right? There's a relationship between 2 variables, and it ends up being a linear relationship. B is the y-intercept. M in this context represents a slope like rise over run. Really know this by heart. Hopefully you do. And if you're rusty on that, then see an example of that later today. Lots of parabolas in physics. Did I tell you guys the example with the keys? You throw the key straight up. No, I think my other class, right? So there's a question you're going to get sometime in the next few weeks that involves like you're down on the ground level and you take your keys and you throw them straight up, and there's somebody up in like the 3rd story window, right? And they're trying to catch them, so you're trying to throw your keys to your friend, right? And if I throw something straight up and it comes back down, right? If I look at its height meters as a function of time ticking along in seconds, this is a time axis. So time's ticking along, tick, 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 right? It actually follows a parabola shape. You'll see lots of parabolas in this class, right? You're going to graph lots of parabolas, right? So the question that the textbook is going to ask you is, when does your friend catch the keys? When does your friend catch the keys? And if you do the math, you realize that there are 2 solutions. And think about it, that should make sense, because the keys could be coming all the way up and you can grab them all the way up. But what if you miss this? Like, then the keys are going to come back down and catch them on the way down. So that's 2 different time values, right? I think this is a good formula to memorize. Is AP going to expect you to memorize it? No. At least, at the bare minimum, at least be aware of like when you could possibly use this, and you'll be able to like Google it or something. But I think it's a good one to have in your back pocket. Common graphical relationships. There's just a handful of graphical relationships that you'll see in this class over and over and over. These are all of them. Maybe there's an oddball graph here or there that doesn't align with one of these. Right? So no relationship. If you increase, say, like this variable, and the other variable just doesn't change. So like, oh, okay. Plenty of examples of that in this class where you like increase the mass and you're testing for something, and the other thing just doesn't care what the mass is. Direct relationship or linear relationship. If you scale up this variable by a factor of 3, then this other one also scales up by a factor of 3, for example. Right? Inverse relationship, you make one variable big, the other gets small. Right? Classic example, you've got 2 objects. Right? Kick this one with some force, kick this one with the same force. So as you increase the mass, the acceleration would decrease given the same force, right? It's an inverse relationship, Newton's second law. You'll see lots of parabolas in this class. Parabola and root is really, you could just swap the axis, right? So what variable you decide to put on which axis, right? These could be, one could be the other depending on what you decide to put on which axis, right? Right. And then next semester in January, when we're dealing with like pendulums, you might get some of these sinusoidal type graphs where it's like oscillating back and forth. Okay. You got some trigonometry here. You guys know Pythagorean theorem, area of a triangle. Areas of triangles are going to be really valuable because you'll find areas, lots of graphs. So like under the curve, they could have lots of physical meanings. So you guys are going to see. Right? This is really critically important, but I think I'm going to take probably Monday or Tuesday to do a whole day at least with you guys on this, and you'll see that throughout the semester. All right, so that was a little bit of stuff I ran out of time the other day. Let's knock out these algebra puzzles. Who figured out what is the answer to this first one? What'd you get? All right, Chloe says 6. You guys get 6, I think. Is that right? Negative 6, right? Yeah. That's what you said. That's what you meant. Yeah. All right. And I don't have the answers in front of me, so I didn't actually know. I forgot. But here we go. Oh, so P, I guess we're solving for P in this case, right? Like algebra is a system for, it translates from Arabic. It's like those systems for solving, right? So usually you're solving for X. There's a whole fun history behind that about how it's translated to Greek. They're using the Greek letter chi and blah, 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 translate. But in this class, you have a whole 2-sided page of variables that I gave you guys. You could be solving for any of those variables. So in this case, I guess like P, right? So I'm gonna subtract 5p over here. I could do it this way. At the same time, I could subtract this 4 over here. So I guess I'm doing 2 steps in one there, right? So I got, see, 3p I'm left with on this side. And what's this, negative 18 over here, something like that. I did 2 steps in one, right? As long as you do the same operation to both sides, it all balances. And the next step is to do what to both sides? Yep, divide by that coefficient 3. So p equals negative 6, right? Good thing to do, especially if it's a really long process and you very well could have made a mistake somewhere in between. I know this one was real short, right? Is check your answer. So take whatever the answer should be, plug it back into the original statement and see if it checks out. But let's try it. Negative 6. Guys, what is 5 times negative 6? Negative 30. Minus 14 is...
Interruption off. At this time, we need you to go into a shelter and play. We move into shelter and play procedure. This is only a drill.
All right, nobody move. We're gonna do some algebra. And if you plug in -6 here, what is 8 times -6? -48 plus 4 is -44. Check it, Deca. Look at there. It's the same thing. Right? I'm gonna show you guys another perspective on this same problem, because that's like an algebra process, right? Like it's like undoing everything that's there until you finally isolate the variable you're looking for. What if I treat these as equations and I'm going to find a graphical solution? What if I treat this as like y equals 5p minus 14, and I've got a separate equation, y equals 8p plus 4. Those could be two different lines. I could graph those, right? See what these graphs look like. I'm not going to make an exact graph, but I'll get it in the ballpark close enough just to get the idea across. So I've got a y-axis here, maybe a p-axis here, right? So traditional math might do y versus x, but in this class, you got any variable and any variable. Let's do y versus p, right? So y equals mx plus b. Can this first one have a y-intercept at -14? Let's just throw that on the board right about there, -14. And a slope of 5, so that's rise over run of 5 over 1. That might look, for example, something like, maybe something like that. Okay. I got 5 to 1 ratio, that rise over run. Okay, so that could be the first one. How about this one? 8p plus 4.
At this time, we need to move into a lockdown procedure. Lockdown procedure is only a drill.
Let me pause this. All right, recording is resumed. All right, so we're all here, alive, made it. You guys did awesome in the drill. All right, so let's graph this guy. Y-intercept, boom, on the board. Slope is 8, so rise over run of 8. It's a steeper slope, so let's do maybe something like this. Like slope is like here, 8 to 1 ratio, right? So this guy's like walking uphill. I don't know, it's even harder to climb, right? But look where those two lines cross. Right? Who wants to tell me what is the p coordinate and what is the y coordinate of that location where they cross? Who knows? Yep. Boom. All right, I'll let you. I bet some of you guys are thinking that too, right? This is at -6. This is at -44. This is the coordinate -6, -44, right? Which is exactly what we got using this algebra method here, right? Graphical solution, same thing, right? What else we got lined up? I'm gonna go a little bit fast, gotta get everything in today, but this one here. Did anybody solve the second one? Solve the second one? What'd you get, Carl? You got it. All right, and how they got 4 too? Right, some of you guys got 4. All right, let's check this out. What's the very first step you need to do to solve for x for this second problem? Distribute. Good call. Distribute. Right. Right. So this -3 is being multiplied by both of those pieces. This 4 is being multiplied by, or multiplying into both of those. Right. So I got, see that, what is that? -12x. We're solving for x. Right. -9. Right. 3 by 3 is negative. Plus 24x, which we're solving for, plus 4 is 43. Okay. At this point, we got 5 terms. Boink, 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 boink. 2 of them have the variable, and 3 of these are constants. So let's start pulling things together. These two x values tied together, that's 12x. I'm going to go -5 is 43. Right. What's the next step? Add 5 over, right? Plus 5, balance this thing. Right? That's going to give me 48. What's the last step, both sides? Exactly. Divide by that coefficient 12. Boom. X is 4. Exactly like you guys said it should be. You can plug it back to the original statement. That's going to be true. Let's do one more algebra problem. That might actually cover us, I think. Okay. My owners classes, maybe I'll ask them if they want to do more of this practice, but I think you guys are going to be good. Right, so I got -8 plus this big old square root, 5a minus 5. Let's say we're solving for a in this case, right? Is equal to -3. Oh, I should mention too, when you make square roots, make sure that your square root bar extends over the entire square root. I'm saying this because I've seen over the years, like many students who just like stop at like halfway, and then like maybe wouldn't include that -5, and then it's really confusing ways. The -5 part of the root or not? In this case, it definitely is. Sometimes it's a good thing to like put a little notch at the end of your square root just to even remind yourself to go all the way to the end of what's being rooted. Okay. Now there's probably one of 2 ways you may be thinking to kickstart this problem. One way is going to lead you to a giant mess, and the other way is like the proper way to do it. What is the next step that you do want to do? What do you want to do? do you want to square both sides, or do you want to add the 8 over? What do you think? Somebody say move the 8 over. How many guys think move the 8 over? Yeah, okay. Here's the thing. If you square both sides first, eventually we're gonna have to square to undo the root. Right? But if you do that first, you guys remember FOIL, F-O-I-L, right? So this is two different terms added together. So if you square the left side first, you'll get, see, this would be 64, and then this times this outside, this times this inside, and then this squared. So you'll still have some square roots hanging around, and it just looks even messier. It's like, okay, so backtrack. Yeah, let's do this other method you guys said. Add the 8 over, okay? Plus 8, plus 8. Right, so I'm gonna, okay, now we have the square root isolated. So now we can like square it, right? And this is all equal to like 5. Okay, so now we can square both sides, right? Square, so 5a we're solving for minus 5 is equal to 25, right? Okay, now it looks like the other ones we did, right? So add over the 5, got 5a equals 30. And then finally, divide both sides by this coefficient. A is, okay. Did you guys get that too? Got that too? Right, are we good? All right, any questions? All right. All right, let's do an activity. All right, so do you guys see this grid page on your desk? I've got some other things I want to do later too, but yeah, again, trying to do something that'd be good for today. I've got this rainy day activity that I know from the past, if I don't do it today, it's probably going to burn a hole in my desk until May. So hey, let's do this here. Right, so I've got a story attached to this. Do you guys see 15 different items? You guys see some different columns. All right, so I'm going to read you guys a story. Some of you guys may have done this before. So, okay. So it goes like this: NASA exercise survival on the moon. So some NASA scientists put the story together. Okay? So the scenario goes: you are a member of a space crew originally scheduled to rendezvous with a mothership on the lighted surface of the moon. Okay, lighted surface on the moon. Keep track of those details. That might help you rank order these here in a minute. However, due to mechanical difficulties, your ship was forced to land in a spot some 200 miles from the rendezvous point. Oh no. During re-entry and landing, much of the equipment aboard was damaged, and since survival depends on reaching the mothership, the most critical items available must be chosen for the 200-mile trip. Below are listed 15 items left intact and undamaged after landing. Your task is to rank order these items in terms of importance to the crew, allowing you to reach the rendezvous point. Place number 1 by the most important item, number 2 by the second most important, and 15 would be the least important item. Did you guys get that? Right, so to point out what's going on this grid page here, I've got all the items listed. I've got your ranking, so you can go down the line. Your team ranking, so you guys can collaborate with each other and determine blah, blah, blah. Right? I'll show you guys the answers. That's the third column here, NASA ranking. Right? And then, okay, well, there's so much stuff after that, but let's get at least that far. So I'm going to leave this scenario up here. I'm going to pause the video and give you guys a couple minutes to rank order those items. Oh, let me give you guys a couple hints. Okay. So one hint that I should give you guys, do you guys see 200-pound tanks of oxygen? Okay. Those pounds, when you look at the solution and their justifications, they're talking about Earth pounds. Guys, up on the moon, do you guys know what fraction of your weight you have on the moon compared to here on Earth? 1/6. Boom. All right. Yeah, Stephen knows 1/6. Right. So 100 divided by 6. Right? Everything's a lot lighter on the moon. Okay. Right. So we're talking about Earth pounds. What else do I want to tell you guys? Let's say the signal flares are able to work. You might think, well, wait, something about combustion, something, blah, blah, blah. Right. Let's say that anything you need for combustion is like contained within the flare. Oh, here's what else I want to tell you guys. Right. First aid kit, including injection needle. If you're thinking to yourself, well, I don't want to go poking holes in my spacesuit. Let's assume that there's like some special aperture that you're able to use the injection needle if you need that. Right. All right, so here we go. Leave that scenario right there. Let me pause this and you guys go ahead and take a couple minutes. Boom. All right, recording is resumed. So you guys had a few minutes to rank for themselves, work with each other. All right, so I'm about to show you guys the NASA rankings and what their justifications are for these. All right. After I show you their rankings, you guys see these last two columns? It says your difference and then the team difference. Take the difference, like the absolute value difference between your score and NASA. And then same thing, your team at NASA, and then record those numbers as you go down, right? You guys only record absolute values, so there should be no negative numbers. Okay? Because at the end, you're going to add up all the differences. Now, if you recorded negatives, then this would necessarily zero out, not what you're looking for. Right? You're looking for absolute value differences. And the lower your score, like the better you did. Right? If you got exactly what NASA got, then you actually would get a 0, right?
Golf.
Okay. Yeah, golf. There you go. Golf scores. All right, you guys get this? All right, so one of the purposes of this activity is to show that supposedly you should see that if you work within a team, you tend to do better than you do individual. That's not always true, but it's pretty consistently true. So let's find out. There you go. Answers. Box of matches, 15. Virtually worthless because there's no oxygen on the moon to sustain combustion. So if you're trying to light a match on the moon, it's not going to happen because that's a chemical reaction that involves oxygen in the air and moon, no atmosphere, right? Right, so I don't know why they brought matches. I don't know if they were going to light them in the ship and light something or what. I don't know, maybe they're doing match puzzles. Food concentrate, 4. Efficient means of supplying energy requirements. It's a very engineer's way of saying people get hungry. 50 feet of nylon rope. They ranked 6. The justification is useful in scaling cliffs and tying injured together. All right, if you get injured, I guess you get tied by 50 feet of nylon rope. Parachute silk. All right, so they're ranking 8, and their justification is protection from sun's rays. Right now, let's think about this a little bit. Remember, I pointed out that detail. We're on the lighted surface of the moon, right? On the lighted surface, right? Now, on Earth, from day to night, the temperature will change a little bit. It's a little warmer in the day. It's a bit colder at night, of course, right? But on the moon, if you're in the sunlight and then you go step in the shadow, guys, how hot is the sunlight on the moon? Is it like being in an oven? Yeah, and if there's a shadow up there and you walk into that shadow, is it like you just walked into a freezer? Yeah, again, because the moon has no atmosphere, right? Now we're on the lighted side of the moon, right? And we're like some 200 miles from the rendezvous point. Oh, I forgot to give you guys a context there, but for like Florida context, it's approximately from here to the Georgia border, right? So that might take a few days. Right? Now on Earth, it might feel like day, night, day, night, day, night. But on the moon, see, we're on the lighted surface, right? How long does it take the moon to rotate once? 1 month, right? Month, moon, same root word, right? So, because you guys know that the moon is tidally locked to the Earth, right? There's only one side of the moon that ever faces the Earth, right? Like before we had satellites, we never even saw the other side. Call it the dark side, but right? I guess it's dark to our vision, right? So put 2 and 2 together here. See, we're on the light side, unless the sun's like setting on the moon at that moment. It could be a good like week or two for sunset. So we're like perpetually in daylight not perpetually, for a while, right? All right, next one, portable heating unit. Okay, now this one, the reasoning goes hand in hand with the parachute silk, right? Parachute silk, protection from sun's rays, like reflective type, right? Like people in the Middle East, like wear like these, like, I don't know what you call it. But heating unit, do you want the heating unit? We're on the light side of the moon. So, do you want oven heat plus more oven heat? Probably not. So that's near the bottom of the list. 13, not needed unless on dark side. Now, maybe they should have said the night side, right? So, if it was night on the moon, I bet that would go way up on the list, right? But I guess the idea of prioritization is, suppose you can only take like half the things, right? Okay, got to prioritize. 2 45 caliber pistols. What do you guys think?
Yes.
Yeah. 11, and the reasoning is possible means of self-propulsion. Maybe something to do with NASA is an American agency, so yeah, we're going to take our Second Amendment rights to very creative propulsion systems. Might be another reason for those, but let's go self-propulsion. Yeah, that's why. 1 case of dehydrated milk. What do you guys think? High or low? Oh, is it chocolate? Was the question? So they're ranking number 12. Say bulkier duplication of food concentrate. Okay, I guess we need the pistols more than food. All right. 200-pound tanks of oxygen. One. Good call. 1. Most pressing survival need. In fact, if you could only take one thing, probably be it, right? The oxygen. And then they mentioned, it would be equivalent 17 pounds on the moon, probably carrying around a couple bowling balls. But all right, but yeah, you got a broom. Stellar map. Are you guys gonna rank that high or low? Stellar is like stars, right? So you got a star map. High or low?
Pretty low.
Ooh, I'm hearing some of both.
So this is the lighted side. It's probably just gonna show you the sun.
Ah, dang! I do need to Google that. What do the stars look like on the light when it's daylight? They're putting it really high. I should Google that. Yeah. And yeah, I know if you're on the night side, definitely you see like the stars like better than ever. But I don't know what the stars look like on the other.
So all the stars are so far away that makes no difference.
Yeah, but the sun is
oh,
overpowering all.
Yeah,
of
we're
that.
just thinking about like you can't see the stars in the day on Earth. So yeah.
Oh, wait, but the no atmosphere means it wouldn't be refracted back into you from the side.
Huh.
Probably could use at least some of it.
Let me Google that real fast here. All right.
Think about this.
Yeah. All right. Can you see stars from moon in daylight? I don't see how that does it. When the okay, so okay, here's what I'm reading straight from the internet, where everything is true. When the light comes from the sun during the daytime, it does not scatter in large amounts like on Earth. So we're talking about on the moon, and it's not able to produce glare like on Earth. That's why we are capable of viewing stars even in the daytime on the moon's surface. Okay, yeah, so that confirms that. Okay, right. So yeah, if you look at the star now, of course, at night we can see these on Earth, right? If you look at the stars, how many guys could like very quickly identify the North Star on Earth? You guys could do that probably within like say 10 seconds. Ooh, some of you guys can, right? If you go back like 1,000 years ago in history, almost everybody could do that. Like it'd be instantaneous thing, right? So at night there's something else going on, right? So you look up in the sky and everyone can very quickly orient themselves. Oh, there's the North Star, there's a bunch of constellations, and they would like immediately know within like a second, like which way is north and east and all that. Okay? So yeah, so this is gonna be our primary means of navigation. Self-inflating life raft. They're ranking number 9. Justification, CO2 bottle and the raft could be used for propulsion. Hey, more creative propulsion, I guess. All right. Magnetic compass, high or low?
High.
Ooh, near the bottom of the list. Right. Because how does a compass work? Well, it's like a floating magnet, and it aligns to Earth's magnetic field. Now, why does Earth have a magnetic field? The main theory has to do with like the fact the Earth is spinning, has like a rotating core with ferromagnetic materials in it. But any like planet or moon that's smaller than Earth is like cooled off like faster. So like Mars, for example, probably had a magnetic field at one time, but as it cooled, eventually solidified, and Mars no longer has a magnetic field. Same thing with the moon. Moon, no magnetic field. Compass is pretty well useless. 20 liters of water.
2.
Number 2, needed for a replacement of tremendous liquid loss on the light side. People get thirsty. Signal flares. The ranking 10 uses a distress signal when the mothership is sighted. Again, assuming that that'll work on the moon. First aid kit, including injection needle. They're calling 7. Needles are connected to vials of vitamins, medicines that will fit in a special aperture in NASA spacesuit. Right. Solar-powered FM receiver transmitter, the ranking number 5 for communication with the mothership, but it would require a line of sight transmission. It can only be used over short ranges. So once we get it close enough, we say, oh, there's the mothership. Now we can break up the radio and start communicating back and forth there. And so go ahead and add up your differences both for yourself and for your team. Give you guys a little time here. All right, and then I'll show you guys the score sheet. All right.
Yeah. Actually, it's kind of surprising. Both the line and
All right, first question for you guys. Did anybody do better as an individual than a team? Anybody? Whoa, bunch of guys. All right. So yeah, that's kind of interesting. All right, so go ahead and take your best score, and let's see, how many guys scored 25 or less? 25 or less. Ready to do that? Ooh. All right, who scored 26, 32? All right. So you guys did good. Who's 33.45? Average. Oh yeah. Who is 46.55? Oh yeah, 46.55. Who's 56 to 70? Also wants to volunteer the score. All right, we got some volunteers. Anybody score 71 or higher? Casualties of the space program. Dying in space. All right, we got just enough time for this last activity. Let's do a little bit of dimensional analysis here. This is just fun activity for you guys. All right, so back up to breaking out your notes. I want to do 2 problems with you guys. Pizza party. Suppose it's you and 13 friends, 14 people at a party. And here's the question. How much money do you have to budget to buy pizza, right, for 14 people? So you start to make some estimates, start to look up some numbers. Oh, you said $63?
36.
Well, we're gonna find out. So suppose you estimate the number of slices per person. You know there are 8 slices per pizza, wherever you're ordering from, and let's say you found some $9 pizzas. This might be dated a little bit before inflation took over. So let's set up some railroad tracks and solve this. Okay, time out here. Let me pause this. All right, recording is resumed. You guys get the railroad track set up? All right. Something like this. So here, let's go through, start solving this. So you guys start with 14 people.
Yep, 63.
$63. $63. How many of you guys got $63? All right, winners. Let's sure. All right, 4 slices per person. So should the number 4 go on top or on bottom? 4 slices per person. On top, or
On top.
slices per every 1 person, right? So that the unit people person's the same unit, right? Right. So if we stop right here, we know how many total slices are being consumed, right? Let's go on, right? There are 8 slices in every pizza. Should the number 8 go on top or on bottom? On bottom, right? So because you're setting this up in such a way that 8 slices per 1 pizza, right? The unit slices cancels out with these unit slices. At this point, we know how many total pizzas we need to buy, right? You might want to check that's a whole number. It is, we're good to go. Right? Remember the theory of why this works, right? 8 slices is equivalent to 1 pizza. So if you make a fraction either way, it's just like multiplying all this stuff by 1. So you're not changing anything, you're just swapping out the units. Right? And finally, $9 per pizza. Should the number 9 top or bottom? Top. $9 for every 1 pizza. Now the unit pizza cancels out, and the only unit we have left on the board is dollars. Multiply across the top, divide across the bottom. The number should be 63, and the unit is dollars. Right? Remember this class, almost all the time, every number should have a unit attached to it, right? Boom. Right, $63. Right, you guys good there? All right, you guys ready for the challenge problem? All right, so we won't have time to finish this in class, but my other AP class, they told them to see if they can solve this by Monday. Let me walk you guys through this. Here's a really fun back of envelope calculation problem. Right? So here's a solar energy problem. Let me jump down to the question. How much land area would you need to supply the entire energy demand for the United States if you just did with solar? Let's say you find a big old patch of land out in Arizona and you just like start building solar panels. Okay. Okay. Now we're gonna say back of envelope calculation because we're gonna cut through some engineering difficulties like like storing the energy, blah blah blah, right? But we'll get a ballpark idea, right? That might be somewhat accurate. Right? So here's the energy demand for the states: 25,000 terawatt hours per year. To break that down for you guys, tera is a prefix. That's 10 to the 12. Right? Now watt is a unit of power. That's like energy per time. It's like joules per second. You guys look on a sort of like 40-watt light bulb. If you plug in a 40-watt light bulb, it's constantly consuming 40 watts. That's like 40 joules per second. H is hours. Ooh, I see a time unit here. I see a time unit here. You think at some point your railroad checks have to reconcile the time units, right? How concentrated is this solar energy? Well, the surface of Earth at noon in the summer, it might be about this 1360 watt per square meter. That's how much power per land area, right? But sometimes it's night, sometimes it's cloudy. So let's take this average of about 400 watt per square meter. Right? 1 kilometer is 1,000 meters. 1 square kilometer is 1,000 square. That's 1,000,000 square meters. About 9 floor tiles, 3 by 3 is pretty close to a square meter. So 1,000,000 of those is a square kilometer. Right? And one last curveball here at the end. Suppose your solar collectors are only 20% efficient. So 100 watts land on them, but only 20 watts actually are useful on the grid. Right? There is enough information lying around there. You can calculate the land area that you need to supply that total energy demand. Ooh, I got that in before the bell. Right, so there you go. I'm going to post this video to the classroom, and I'm curious to see how many of you guys are going to solve that by Monday. All right, you guys have a great afternoon.